Welcome to Section 3 of Built-Up Roofing Damage Assessment. In this section, we're going to look at some of the design and application issues on built-up roofing. First, we're going to look at the flood code application. Then, how you terminate the edges of the roof. Some of the flashing issues, appurtenances, and then what happens when the membrane starts to slip. In order to talk about the bitumen, first we're going to talk about cookies, everyone's favorite subject. We know when you bake a cookie, that's going to drive moisture from the batter. There is that optimum baking quality where the cookie still has that chewiness. If you continue baking though, that's going to drive more and more moisture out of it. There's going to start becoming shrinkage of the cookie. It's going to start to crack and become brittle, and that's not good for anyone. Similar analogy to our flood coat. There is an optimal temperature of application. There's optimal thickness of the flood coat. So you can have too much or too little. The ideal is about 1/8 of an inch thick, which applies at about 60 pounds per square. In the photograph on the left, we see where too much thickness of flood coat was applied. This may have been because the temperature was too low. When it's too thick, there ends up being more net shrinkage with time. The cracks become more numerous, deeper, and wider. And this is called an alligator cracking pattern. If you have not enough flood coat thickness, it's too thin, and then with exposure to UV and moisture with long term, it'll start to wear, and that's what's shown in the photograph on the right, that the fiberglass matting of the felt ply is starting to show through. The edges of the roof are called terminations, or if there's gravel on the roof, a gravel guard. When you get joints between two adjacent metal pieces, that's going to be a stress concentration point. And often, the roofing on top of it will crack and split. And so if there are reports of leakage in the building, especially along the walls, that's a good place to check for cracking or splitting of the roof. Often this is when there's just one ply of roofing installed over the metal. The graphic on this slide shows a proper gravel stop detail from NRCA, where the multiply built-up roof goes underneath the metal. The metal is installed on top of it and is fastened in place. Primer, it gets installed over top of the fasteners, and then it shows 2 layers of stripping plies attached over top of that edge metal. And that would give enough strength to withstand those thermal expansion contractions at the joints in the gravel stop. The photograph in this slide shows where there was no edge metal installed at all. It was a concrete roof deck. It did not have any primer, and as such, the built-up roofing did not attach very well. It could be lifted right off of the roof deck. Obviously, water infiltration, poor attachment, many issues were found on this roof. With a concrete deck, you need to apply a primer before you would apply your asphalt or adhesive for attaching a built-up roof. Whenever you have a roof intersecting with a wall, you have to do a vertical flashing and terminate that with some edge metal. Any type of opening, gap, joint situation has to be looked at as a possible pathway for water infiltration. Often that base flashing is a single ply material, and so if you've got an opening such as is seen in the photograph on the left, or it's starting to fall down like the one on the right, that is a direct pathway for water infiltration into the building. On top of the parapets, we've got the metal coping. To make that coping as watertight as possible, the fasteners should be installed through the vertical portions as shown in the detailed drawing on the left, and not how it's done in the photograph on the right where there's several fasteners through the top of the coping. Another way to improve the water shedding performance of the coping is to have some slope on it. It should slope inward to the inside of the roof, where then the water will be handled by the normal roof drainage characteristics. When you have 2 pieces of coping intersect, the ideal detail is to have a cover or butterfly flashing that would go over top of them, as shown in the photograph on this slide. That butterfly flashing accommodates movement from both sides, and so you don't have a stress concentration point. The parapet shown in the photograph in this slide did not have metal flashing or coping installed to it. There is some type of sealant material there, but with time you would expect this sealant to crack, and concrete or CMU blocks are fairly porous materials, and so this is not going to be a very good long-term performer for water resistance. In looking at drainage systems on flat roofs, there really should be a primary and secondary drainage system. In the photograph on the left, we see the primary drainage is through an interior drain. However, secondary drainage is there in case that primary drain gets clogged. This one is installed too high. I can imagine that roof collapsing before the water would get to the point of that secondary drainage in the wall. In the photograph on the right, we have a similar situation. There already is water ponding on the roof, and there's still several inches to go before that water would reach the secondary scupper opening in that parapet. The ideal distance is that secondary drainage would be about 2 inches above the roofing field. And so at that point, the water could get to the secondary drainage without causing a roof collapse. Here's another example of primary and secondary drainage systems. The drain on the left is the primary, and the drain on the right is intended to be the secondary, and the white drain pipe extends up higher. This one extends up too high, though, and the ideal would be 2 inches. This one looks to be approximately twice that height. The one thing that is proper in this photograph is that there is a built-in strainer to both of the drains to help keep debris from clogging the drain system. These photographs show the lack of a proper strainer. There is a metal screen that's there that is somewhat attached. This is intended to be a drain, even though it's a very small opening and there's really no detailing at all to it. This photograph shows a little more highly designed drainage system. We've got the strainer, and we've got the drain actually separated from the gravel ballasted portion of the roof by a weir. There are slots in the perimeter of this pan to allow the water to come through, but to keep the gravel out. So this one is well thought out as far as trying to keep the drain free flowing and moving. When you have multiple roof levels, you may be having water come from one roof level down to the other. The photograph on the left is a poor detail where the water is just coming out of a downspout and it is scouring away the gravel and the roofing surface. On the right, a better detail where there's a splash block at the bottom where the water will discharge and then get onto the roof system. Another source of continual water can be air conditioning units on the roof. The building code will require the condensate coming out of an air conditioning unit to be piped off the roof. Though this is commonly not done, and as shown in the photograph, you have that discharge where condensate can drain onto the roof. This can keep the roofs consistently wet during the wetter portions of the year. Whenever you see fasteners surface driven into the roof, chances are that was not done by the original roofing contractor. That can be done by later maintenance, other type of appurtenances or equipment that's added onto the roof. In the photograph shown in this slide, we have circled areas where fasteners are driven directly through the roof system, and there's no proper flashing there. You've got serious concerns for water infiltration in areas such as these. The roof shown in this photograph has gutters, and then the straps for the gutters were attached directly into the roof system, another pathway for water infiltration. When you're trying to get conduit lines from the outside to the inside of the building through a roof, often you see a detail known as a pitch pan. Though pitch pans are not preferred by NRCA or ARMA because normally they become a maintenance issue and they are frequently cause leakage into the building. The photograph on the left of this slide actually shows where a air conditioning unit had been in place, it's been abandoned, but yet the pitch pan remains and can continue to be a source of water leakage for the building. The graphic on the right shows what potentially would be a better detail for the pitch pan. Here we've got some examples of pitch pans we've seen on the roof, and you've probably seen them too, where you've got multiple lines coming in, you've got gaps and cracks in the pitch pan, and many possible sources for water infiltration. These pitch pans are seeing many different penetrations coming through them, especially the one on the right where it looks like about 10 air conditioning units are having their conduits run through a single pitch pan. A pitch pan of that size is going to have a lot of sealant, and just like a thick application of flood coat, the thicker the sealant is, the more it's going to crack and become a source of water infiltration on the roof. There are many other examples of inadequately detailed appurtenances and penetrations that you're going to see on the roof. Here's some examples on this slide where there's no apparent flashing at all, just a hole being cut into the roof and then sealed with plastic roofing cement or coating around them. If roof leakage is being reported in the building you're inspecting, you need to find out where that is on the inside, and then when you're up on the roof, you can look for details such as these that would show you potentially where the water is coming in or trouble spots. Are there better ways to do it? Yes, there are. The photograph in this slide shows a particular proprietary system that's for getting conduits going through the roof. It can be stripped into the built-up roofing, and then it's got a watertight seal for the actual pipe conduit to go through. When you have large commercial buildings with flat roofs, often there's piping systems across the roof. Metal piping will have thermal expansion as well. The photograph on this slide shows a detail that would accommodate well the thermal movement with the pipe support systems. So this is a good example. One thing you expect to see when inspecting built-up roofs are membrane blisters. They can be in various sizes and shapes. The blisters result from skips or voids in the original mopping of the asphalt. And when you've got that dry spot or void, moisture can get in there. Once that moisture vaporizes, its volume greatly increases from its liquid volume, and that will cause this bubble or blister in the roof. Another cause for it is if you've got a second roof installed over what was originally a wet leaking roof, then that roof may have moisture in the system, and that may cause these bubbles or blisters to form in between the two roof systems. One consideration when dealing with blisters during your inspection is to be careful with the foot traffic. They are a weakened area of the roof with limited support. And in the photograph shown in this slide, a broken blister has occurred from foot traffic. They also are more susceptible to hail damage. So if you do see a blister, treat it gently. You may want to press lightly on it with a foot or with a hand to find out if the blister is intact. Because a blister does not mean there's a leak if the membrane is still complete. But if you press on it and you hear air escaping or you see water squeezing out, that shows you that the blister already has fractured. Some blisters can be quite large and high, as we see in this photograph. When blisters are very elongated and narrow, another term for them is ridges, and these narrow ridges also are going to be quite sensitive to hail impact or foot traffic, and so best not to step on those at all. Just try to get over top of them. The pattern shown in the photograph on this slide is known as picture framing. You see rectangular shapes, and they are mirroring the shape of the insulation boards below this smooth surface built-up roofing. The ridges that have formed show that the insulation board has had some dimensional stability issues. It doesn't mean there's a leak, but that is the reason for this pattern. When blisters on the roof are going in meandering various forms, they're known as mole runs for the appearance that we see in this photograph. A fish mouth would be an open end to a wrinkle or blister. Our built-up roofing system is a multi-ply system, but whenever you have a fish mouth like this, you've at least lost one effective ply to your roofing. And likewise, you have to look to see if there's any type of impact damage or foot traffic damage with a fish mouth such as this. To repair it, you'd have to cut it out, flatten it out, and get it sealed or hot mopped. When a built-up roof has slope to it, and the steep or special steep asphalt is not used, you can have situations where the roof actually starts to move or slide downhill. One indication of this is shown in the photograph on the left, where you've got parallel diagonal wrinkles in the base flashing on the parapet wall. The photograph on the right shows actual splits and wrinkles that have formed in the built-up roofing as it's pulled away from the upslope wall on the right. This photograph shows the breaking point where that asphalt that was not solid enough or viscous enough actually started to separate at that membrane ply and has moved downhill about 1 inch. This concludes section 3. Now it's time to go to your review and quiz. Thank you.